All right, today we're going to look at sequences. Now, sequences can be presented to you in a number of different ways. We could have images. Maybe image 1 has so many blocks, image 2 has some number of blocks, image 3, and we're trying to look at the pattern in the sequence. We could be presented a sequence in just a set of values, no images. But realistically, what we're trying to do is find the pattern of how the sequence is built so that we can find future values or maybe the next value or whatever it is that we may be interested in. So one way to do it would be to create a recursive formula. A recursive formula would be to start off with a certain amount of values or a certain number of blocks, and then if we can recognize the pattern on how to go from the first image to the second image, and then continue that pattern by saying, I'll take the second image to get to the third image, use the third image to get to the fourth image, then we could essentially recreate any value that we want by continuing that pattern. But in some cases, maybe we don't want the 6th image or the 7th image. Maybe we want the 50th image. So to go through one value at a time to get all the way to 50 would be very time-consuming, right? So this is where an explicit formula for a sequence would come in handy. The idea of explicit formula is to create a formula for the sequence where we can just say whichever value or image that we're interested in and get the number associated with it. So if the 5th image had 11 blocks, then if we knew how to build this sequence, we can go right to the 50th image and say how many blocks are in that guy. That's what we want to do today. So if you are interested in the recursive formula for this, there is another video you can watch to go through that one. But this one is specifically about the explicit. So for starters, we need to know how the pattern is growing because we can't anticipate future values without seeing how things are being built. So we can work with differences or products to see, how to get from one value to another. I'm going to look at differences, so we can say, well, what do we do to 1 to get it to be a 2? Well, we can add 1. What can we get 2 to be a 4? We could add 2. And proceed down. 4, we know plus 3 would be 7. 7 plus 4 is 11. Now, if all these values were the same, we know that the function would be growing at a constant rate, which means it would be a linear function. But I'm going to be interested in quadratic sequences for this video. So this would be a linear function. We would set this up a certain way if all these were the same to be a linear function, but obviously this one's not. So what I'm going to do is I'm going to go and look for the second order difference. I know that the second order difference would be essentially the differences between each of these values that are changing. This would be a plus 1. I could say 2 plus 1 is 3. 3 plus 1 is 4. So there we go. This second order difference is the same, meaning that our sequence will be quadratic. Now, the standard form for a quadratic function will be ax squared plus bx plus c. So a, b, and c are constants. X is a variable, right? In this case, we're presented with n's and a sub n's. So we could say that if we picked an n, we should get an a sub n out. So we would get the number of values in a specific term. If we took, I'm going to still use a, b, and c as coefficients or constant values. So we can say a with an n squared plus b n plus c. Right? So our goal is to figure out what a, b, and c need to be to create this formula that will allow us to find any term that we're interested in. So for starters, the largest degree term, right, which is based on the exponent, 2, his coefficient is directly linked to this second order difference. So what we can remember when we're going through it, something that you can just keep tabs on every time you're going through this, is that we know that the A value will always be 1/2 of that second order difference. So since our second order difference was 1, we know that our A value will be 1/2 of 1, which in this case is 1/2. So we know that the constant, right, the constant value in front of this n squared term will be 1/2. Now, the C value will be the next value we're going to want to look for. In terms of a function, we know that graphically, if we wanted to think about where these points lie on the graph, if we plugged in a 0 for an x value, that will put it right here on the y-axis, then whatever value we get out will be the y value when x is 0, right? This will be a y-intercept. So C value will always be the y-intercept, because if we put 0 in and square it and multiply it and put 0 in and multiply it, these guys are all going to be 0, and we're going to be left with a C value. So we know that when x is 0 in our function, right, y will always be that constant value. Now, the problem is we know that n or x is 1, 2, 3, 4, 5. We want when n or x is 0, which would be essentially the value right before it. I'll put it up here. So if we knew this guy that went with it, then we would know C, because he would be the y-intercept. Now, we do know the pattern of how this thing is growing, so this pattern of growth should occur in terms prior to it. So we could say that if this thing keeps growing by 1, it should have been growing by 1 before it. So this second order difference should still carry on if we move along here. Now, do keep in mind that this is a second order difference. So we would have to say that this first order difference value, whatever he may be, this first order difference value, right? If we add a value to it, we know it has to be 1. So we can say, well, what would be this first order difference value such that if we add 1 to it would be 0? So what plus 1 is 1, right? Well, that would be 0, because we know that 0 plus 1 is 1. So this is the first order difference. That means that whatever the y value is when x is 0, we're going to add the first order difference to go from this y value to this new y value. So if this guy is 0, what value would be here to where if we add 0, we would get 1? Well, anything plus 0 is itself, so this has had to be a 1. So when x is 0, y is 1, that means our C value is 1. So I'm going to go ahead and plug some of these things in. I know that the A sub n value can be found by using this formula for explicit. We found that A is 1/2, so it'll be 1/2 n squared. B we don't know, so I'm going to leave that as a B. And C we found was 1. Now, n would be whichever term we're interested in. A sub n would be the value of that term. But we do have lots of n, A sub n combinations. So if this was to actually hold true, if I selected one of these n's to go into these n spots, then as long as I pick one of these A sub n's that goes with it, then this would be a true equation. So I'm going to make my life easy, and I'm just going to pick this first term, right? If n is 0, so anywhere I see an n, I'm going to plug, when n is 1, any place I see an n, I'm going to plug a 1. This is just my select. I still don't know what b is, but I'm going to pick n as 1. But I know that if n is 1, the a sub n value should also be 1. So if I select 1 here, I know if this is going to hold true, which it should because it was given to us, that this guy would have to be a 1 as well. So in this equation, we have enough information to solve for this b value. So order of operations, just be careful with order of operations. 1 equals 1 squared, which is 1, times a half. Now b times 1 is just b. I don't need to write 1b plus 1. Now, if you don't really want to deal with this fraction, that's okay. We want to isolate this b, so I'm just going to subtract this 1 over first and kind of leave the fraction alone for now. I mean, 1 minus 1 is 0, and if I'm looking to solve for b, if I subtract a half from both sides, then b must be negative a half. So we have our a value, we have our b value, and we have our c value. We know this is the generic setup for an explicit version of a quadratic function. So we want to be able to find any term that we want, by using the formula where a is a half, so I'm going to say 1/2 n squared minus 1/2 n, right? Plugging that in for b, plus c, which we found was 1. So I'm leaving n and a sub n alone because if I wanted like the 50th term, if I plug in 50 for the n's and work this out, I'm going to get the value that represents the 50th term. And if you're not sure if this works, you can always try it, right? I mean, we used 1 for n and a sub n as 1. I mean, we built the sequence off of the pattern, but I could easily plug in like 4 for n, right, here and here. And if I put this all together, it should give me 7. If it doesn't, then something's not right. We messed up somewhere. Right? All right, let's try another one. So again, we have this sequence. We need to see how the sequence is being built. So I'm just going to check differences, common differences. So what would I do to -3 to make it into a 3? Right, that would be adding 6. What would I do to make it a 13? That would be adding 10. This guy would add what, 14? 27 plus what is 45? That should be 18. So again, not linear, but if I check the second order differences, plus 4, plus 4, plus 4. It's looking good. This is quadratic. So again, I know, I'll use these notations. I know that I can get any function value, right, by taking a basic quadratic setup. This would be standard form for a quadratic, right? I just need to figure out what A, B, and C are. Now remember, the second order difference directly relates to A. A is going to be 1/2 of that second order difference, which in this case is 4. So that means our A value, half of 4, is 2. The next easiest value to get would be C, because C is the y-intercept. So again, I don't have the y-intercept. I would need x to be 0 here. I'll just put it up here. I need x to be 0, and I want the y that goes with it. But again, we're going to follow this pattern. I know that this second order difference will still be a plus 4, right? I know that whatever this first order difference is, if I add 4 to it, I should get 6. So essentially, what plus 4 equals 6, if you want to write it out, this gives you something to actually physically solve. It's some tangible equation that you don't have to guess the numbers. 6 minus 4 is 2. So if I add 2 here, you could check it. 2 plus 4 is 6? Yes. So this is the first order difference. So what would I need to add 2 to get -3? So again, I could do this again. What do I need to add 2 to get -3? So if I subtract 2 from both sides, we can see that this has got to be a -5. So is -5 plus 2 -3? Yes. I know that negative 2 plus 4 is 6, so this pattern continues. That means our C value is negative 5. Now, B, again, doesn't have any sort of direct relevance to the sequence itself in terms of values that stand out, but we do know that X and Y values should make this equation true. So since we know these are on our function, we know that they should make our equation true. So let's start to build this, right? So I know that f of x is going to be equal to 2x squared plus bx minus 5. I'm going to pick whichever x and f of x value I want. Now, if I want to pick 5 and 45, go for it. Plug it in. It's going to be bigger numbers. It's going to be more work. X's being 1 makes it easy to square. It keeps b just a 1b. So I'm going to keep picking this guy because it's going to make my life easy. Right? So when I take that value and I plug it in, I know that the f of x value is negative 3 when the x value is 1. So it should be 2x squared plus b. I'm plugging in 1 again. Right? Now we're ready to solve for b. We have enough information to make this equation true by solving for b. Again, with order of operations, 1 squared is 1. 1 times 2 is 2. b times 1, not much going on. That's why I selected 1. Still the minus 5. So I could put these two together, right? 2 minus 5, right? It's negative 3. And then if I want to solve for b, I can add 3 to both sides, so b ends up being 0, which is no big deal. We're building our standard form. A is going to be 2, b is going to be 0, c is going to be negative 5. So my function is going to be ax squared. Now, I could say plus 0x, but that's not necessary, so I'm just going to leave that off. Plus c, but c is a minus 5. So here's our function, explicit version, and we can get any term that we want. All right, let's try one more. Okay. So if you want to check to make sure you're getting this, you can always pause the video, give it a try, unpause it, make sure that we're both on the same page. But I'm going to go ahead and jump in here. I need to know the pattern. What can I do to 6 to make 5? I'm going to subtract 1. What can I do to make 5 into a 0? Subtract 5. What can I do to make a 0 into a 9? Subtract 9. Negative 9 minus 13 is 22. So again, it's not linear, right? Going into this not knowing that it's quadratic, I mean, I told you they were all going to be quadratic, but right, if I wanted to check the second order difference, right? Negative 1 plus what is negative 5? So again, negative 1 plus what, if you're, negatives throw people off sometimes. Negative 1 plus what equals negative 5, right? So if I add 1 to both sides, you'll see it's got to be negative 4, right? Don't just assume and you kind of quick go through it, right? If you need to write this out to get these values that are supposed to match up, so be it. Negative 5, I can subtract 4 again. Negative 9, I can subtract 4 again. So we can see that it's quadratic, right? We know that the explicit form for a quadratic sequence is going to be, I'm going to use y because that's what they gave us, ax squared plus bx plus c, right? Now again, our second order difference, a is equal to half of that second order difference, which in this case, a is going to be negative 2. Next easiest value would be to find c. I'm just going to backtrack our pattern here. I know that this other second order difference should be negative 4 if I keep up with it. I'm trying to find the 0 value, which is only one step away, nice and easy. What would I need to do to make this guy fit the pattern? So what value minus 4, right? What value minus 4 equals negative 1? Again, if you need to write this out, no big deal. Add 4. So we got to add 3. So if I add 3, this will be the first order difference. So what value plus 3 is 6? That would be 3. So C is 3. All right. So now we're going to try to find the y and the x values, right? We're going to use these. Again, I'm going to select the x value being 1. It's going to make my life easy. So I'm going to plug in 6 in for my y. So if 6 is y, right, we already know that a is negative 2, so I'm going to plug that in. The x value that went with that 6, right, is 1. So that means that if I want to use 6, I got to let x be 1. B, I don't know. But again, I chose x to be 1, so I'm going to plug that in for both of these. C, we said, was positive 3. Now we have enough information to solve for B. So, 6, nothing going on here. Remember order of operations, 1 squared is 1 times negative 2 plus b plus 3. Try to get b by itself. I'm just going to go ahead and add like terms. So 6 is equal to negative 2 plus 3 is 1. Then I can get b by itself by subtracting both sides by 1. So in this case, our b value is 5. So we did it. We got A, we got B, we got C. We're going to plug them in here where they belong, make our formula. So y equals, I'm just using y's because this is how they presented it to me. We said what? A is negative 2, so negative 2x squared plus b is 5, so plus 5x. C was 3, positive 3, so plus 3. And there we go. Explicit version of our quadratic. Right? We knew it was a quadratic because it had a second order difference. Again, if you're not sure, you're not feeling right about this, I don't know if I did something wrong, I'm prone to making mistakes, pick a number like this. We can take that 5, we can plug it into our x's in both spots, and if we do that, we better get a negative 22 out. You know that if that doesn't work, then something's not right here. All right.